Might be, it might be on an older list. He's really going to get a bigger folder.
All right. So, once again, we're a little behind.
Gordon, you were so vain.
So here's what we're going to do.
Yes.
One new thing.
We're going to skip over talking about the options at Tri-Town right
Ed
now.
is on the former peer committee.
We're really
I
going to
knew he was
focus in
another
on
one.
really what's time sensitive to prepare us for the hybrid meeting in 2 weeks. So, while clearly decisions at Tri-Town are important, we're going to we don't have to have that discussion today. We can have that discussion at another time. We're going to talk very briefly about collection systems, and we're really going to just hone in on a couple of them and not go into tremendous detail. And really focus in on low pressure and step steg. You have more information about the others, and we can discuss questions if you have them. And we want to try and keep that conversation to 20 minutes, 30 at the most, and then we're going to move into talking about PRVs. Okay? So that's our goal.
Did you say we're going to come back to the other stuff we're missing?
Not today.
No, I
Yes.
understand that, but
Absolutely. Absolutely.
Christmas Eve maybe?
Yeah, exactly. Midnight tonight,
When
we'll
you're
see
the
you
only
there.
one here.
Okay, so just a quick rundown on collection system components. When we talk about collection systems, that can mean a number of things. We have gravity sewers, low pressure systems, step stag, pump stations, force mains, all components that can be in any different number of collection systems. So we look at each of these components as just a tool. It's a tool in our toolbox. Got to look at each area and each situation quite differently and determine which is the best tool to use in that location. So we'll just jump through a couple of those components. Don't want to spend a lot of time on gravity sewers. I think a lot of people are familiar with those. Maybe the one takeaway on this slide is, a good rule of thumb, minimum diameter that you want to put in on a gravity line is about 8 inches. And that'll give you a minimum slope of carrying capacity of a little over 500,000 gallons a day. Just put it out there. Some of the advantages, disadvantages, lower O&M costs, but it could be deep excavations, open cut excavations, maybe more expensive installation. But gravity sewers are less prone to plugging because their diameters tend to be much larger. So moving on to some of the stuff that maybe you aren't as familiar with. Low pressure systems. So what these can look like is each entity or home would have a grinder pump. They'd be located in a small tank that would provide a little bit of storage. Typically, it's either in your basement or just outside your house, so that wastewater can flow by gravity into the tank. The grinder pump is controlled by a set of floats, so once it fills up, the pump kicks on. Once it's pumped out enough, the other float turns it off. So it's pretty simple. They typically can use a lot smaller diameter pipes, 2 inches coming out of your house. They pump into a common force main in the road that collects it from all the other homes. There's a series of check valves to make sure somebody else's pump doesn't backflow into your system. The installation's kind of uniform. You don't need to, it's not relying on gravity when it gets to the pump. It can pretty much follow the contours of the ground, and you just need minimum cover so that your pipes don't freeze. Anything else on this one? So it can be installed either open cut or directionally drilled. A lot of these are directionally drilled, but depending upon how many you're doing and the distance, for very short distances, it doesn't make a whole lot of sense to do a directional drill. But for longer distances, it can save you a lot of money. What do these systems look like? There's a couple different ones that come out there, but they're all pretty much similar. You can have either 1 or 2 pumps in a small tank. these are the floats I was referring to. You have an on and off, and probably an emergency. So if if you hit that float, you know that something's wrong. The pump didn't come on, and you have to alert someone to go fix the problem. You'll have isolation valves so you can pump it out and maintain your system. A check valve to make sure stuff doesn't come back in. There'll be one here. There's probably one right above the pump as well, just for redundancy. A little control panel with an alarm light to know that there's something wrong with your system. But in a nutshell, that's basically what they are. So some of the advantages. So since you're putting these in the ground new and you're not connecting anything that's not under pressure, they're much less susceptible to infiltration and inflow. Really, the only sources might be if you have an illicit connection into your collection chamber. That's not typical. Smaller diameter pipes, so you don't have to put in the larger diameter pipes. The pump grinds up whatever comes in there so that it can pretty much not clog a smaller diameter pipe. Like I said, it can be installed open cut or directionally drilled, so that gives you some flexibility. So you can just choose the cheapest option depending upon the situation at that time. The directional drill option can help you reduce disruptions to streets and sidewalks. You can go right under things and not have to worry about restoration after the fact. So from that standpoint, it can be attractive depending upon the route and path in which you have to go to get to where you need to be. And minimal pipe bury depth. So in comparison to gravity sewers, which you have to maintain a slope, and depending upon the terrain, sometimes they can get deep. With this, you don't have to worry about that. You just have to hit the minimum buried depth so that you don't freeze your pipe. Some of the disadvantages with...
Oh, no, go ahead, sorry.
Some of the disadvantages, if there's a power outage, there's limited capacity in your pump chamber, so you have to be cognizant of that. A lot of times when there are low pressure systems in towns, the municipal entity will actually come around and pump you out during a prolonged outage, so that you can continue on. If there is a prolonged outage, there can be a situation where when the power comes back on and all these systems try to turn on all at the same time, they're all going to be trying to pump down the same force main, so they're going to be fighting against each other. Some of these pumps, depending on where they're located, might overload, they'll trip out, and then they'll have to be reset. And usually that's all automatic, but it can delay your pump out. You do have to, it is a mechanical device, so the pump needs to be, maintained properly. You can be damaged if something that shouldn't go down the line does go down the line. A lot of these grinder pumps they're pretty good. They'll chew up most things that come down there, but we do know of installations where they're well aware that these systems can be damaged, and in some instances, it's an educational thing. Don't put certain things down to damage your pump, your system. Sometimes the municipality will say, okay, well, you didn't know the first one's free, but the next one's going to be on you, and that's different. It varies from town to town. So it's an educational thing. People need to be aware that it's not bulletproof, and you have to provide energy to power the pump, as opposed to maybe a complete gravity system. It wouldn't require any energy to flow out from your home.
So sorry, I'm gonna...
Just a quick question on that exact point. Do you know pretty much how much energy is consumed by each unit, and is that typically a private cost or a municipal cost?
Typically, it would be to the individual. It would run off their electric service. Depending upon the situation, you could have a 1.5 horsepower pump, a
Okay,
2
so
horsepower
it's
pump.
Not big.
Not huge.
Okay, thank you.
Typically, as I understand it, the volume of the container is about 75 to 90 gallons for a home.
Mhm.
Is that fair?
They have different systems with different sizes, but yeah, they range from like a minimum size
Okay,
to...
so if you have a power outage for 3 days,
Right.
even if you cut your water consumption in half, 2 people in a building, it's not gonna last 24 hours.
Right, that could be a problem. That's why in some instances, when you have a lot of them in a town, the town may want to provide a service where during a prolonged outage they come. They even they could hook up a generator to your system so that your pump can pump out.
And that's a cost and an aggravation.
Right,
and so
it is. Yes. Yep.
Yep.
Just to throw up some of the information that is available out there on these types of systems. The manufacturers themselves have some case studies of their own, which they've done some white papers on, Parrish, New York, West Monroe, New York. So that was some of the closer ones. Stantec has had experience in Maynard and Bridgewater, Massachusetts, where they have low-pressure systems in their town. It's not the whole system. They're just, there are smaller sections of towns that use low-pressure systems.
Have you talked to anybody at these places?
Well, obviously at Maynard and Bridgewater, we have regular communication with them regarding their systems. So yeah, we have talked to them.
What about the others?
The other ones up top, those are not our clients. We haven't reached out to them since we had enough local experience to kind of get a flavor for how people generally
Are there
operate them.
telephone numbers available to talk to people in these places?
Oh, I'm sure they are, yes.
Could you get
But you
them
did
to
say
us?
those were manufacturers.
They are a manufacturer's one, and it was up on the manufacturer's website, so I hesitated to use a manufacturer's reference.
Do you have a contact, can you get a contact at each of these locations where they're used?
Yeah, I would.
Get it to Mike and then to me?
Sure. We can check in with the folks that we know. Sure.
And I'd be willing to share information I have on grinder pumps as well. I'll send them to you, Mike, and you can transfer them.
I want to try and hold most comments and discussion until we get through this.
Okay, moving on. Next subject. SEG. So, for those of you who may not know, septic tank effluent is where that comes from, and then it can be conveyed either by gravity or by pumping. Now, if it was going to be by gravity, you just have to make sure that the septic tank invert elevation is is sufficiently above, the gravity collection sewer that you'd be discharging to. So, most of the systems that we would probably talk about, and I think we'll reference later on, are all pumps or step systems. And some of the components in step are very similar to that of low-pressure systems, except we do utilize a septic tank that is already on site in a step system. So the effluent from a step or steg system is typically low in solids, because most of them settle out in the septic tank, but it can be higher in nitrogen and phosphorus leaving that septic tank because of what's going on with the breakdown of solids in the tank.
Quick question, quick comment, Lou. In my work in that area, the goal is to use the existing septic tank. However, when the contractors get in there, a lot of the existing septic tanks can't be used. There's a significant percentage that are not in the condition or configuration that can actually be used because they're old or whatever. So that's the goal, though.
Right. That is the goal. And that'll show up in one of the advantages is being able to reuse that. So a little graphic. So similar to what you saw, maybe a little control panel outside your house, your septic tank in here. You're going to have some sort of wastewater pump to pull the water out of here. This is a step. This would be an example of a step, and it would be a low pressure line that goes out to a force main in the road. So all just with the minimum berries required there. So some of the advantages of these types of systems, like Mike just said, the hope is to utilize existing infrastructure with your septic tank that's already in place. So the effluents are lower in solids and less likely to clog any of the lines that you're using. It is lower in BOD and TSS because a lot of that settles out right in your tank. And again, step can be installed either open cut or directionally drilled. However, whatever would be best suited to that site to keep costs down. The minimum pipe bury depths, because of the fact that you're doing a low pressure system out of the pump. The smaller diameter piping And again, the less disruption to street sidewalks and driveways with the directional drilling. Some of the disadvantages, septic tanks, they have to be in appropriate condition, they have to be maintained and leak repaired. There's operation and maintenance on the pumps themselves. Again, a damaged pump from improper waste entering the chamber can be a problem. Effluent quality is low in carbon, so all the solids settle out. So it's low in carbon, but high in nitrogen and phosphorus, which we stated before. But what that does, it makes it a little bit more difficult to treat the effluent when you're looking to, hit a low nitrogen level. You're starting with a higher number, and since there's no carbon in your wastewater, you actually have to add it at the treatment plant to help you in the removal process. So it makes the treatment process a little bit more difficult. There are odors associated with these systems. The water coming out of these systems, as it comes from a septic tank, can be very corrosive. So where it does eventually hit some sort of gravity collection system, there can be a lot of odors and a lot of corrosive problems because that's the first time it actually sees air, and it can be a problem. And again, it takes a little bit of energy to operate the pump. Some of the case studies. We did reach out to Gloucester, Mass. They have over 1,200 connections. And in talking with the city engineer, he did not have a good experience and is not having a good experience with these systems. He's finding that he does have corrosion problems, he does have odor problems, he does have maintenance problems. It was more expensive than they thought it was going to be. So that was one reference. We did reach out to Kennebunkport and Scarborough, waiting to hear back from those folks.
Maybe get to,
I think that's it, yeah.
Well, just for a comparison of the two, the low pressure and, for the sake of this question, step, the throw on the pumps. With the low pressure, we seem to have 75 or 90 gallon tanks. I'm assuming that's then a 60 or a 75 gallon pump each time it cycles. With a step system, what is the throw? How many gallons per cycle? Just trying to get a downtime feel.
They pump about 1 to 2 hours a day.
Right. In the reported capacity, if a power outage, like from the manufacturers of these step systems, the reported capacity is about 200 gallons during a power outage. So there's sufficient freeboard that they build in so that you would have about 200 gallons of excess capacity.
Thank you.
That's coming from the the main manufacturers of these systems.
Exactly what I was trying to get to. Thank you.
This is a very limited number of references to step systems. I have sent to Mike, and I've accumulated a huge number. There are many over 1,000 gallons, 1,000 connections. I've sent them to Mike. I'll send them again to Mike, and he can send them to you. This is a very poor list. In terms of the corrosion, I want to finish it. In terms of the corrosion, that has happened in a few systems where septic tank effluent is combined into a gravity sewer before it gets to the treatment plant. But most properly designed systems do not do that. They go directly into the treatment plant, and corrosion is not an issue.
Well, it would be an issue at the treatment plant. That's just what it shows up somewhere. But yeah, right.
Why would it be? It goes into a tank and it goes there and it's get processed. Why would there be corrosion from it?
That's the feedback that we're getting from the installations.
You know, Mike, one of the things that Ed and I have recommended is that we, as a group, talk to people who run these things and listen to people who are knowledgeable about them. Not just me, because I've talked to a lot of people about this. And unless we do this, we're all going to come away with the wrong perception.
No, I agree with you, Paul.
You could get them on a conference call.
We can get Provincetown in here, if you'd like.
Provincetown is the wrong place.
However, in general, the problem is the vendors of these things have a horse in the race. They have, their reports on these things will be positive.
I'm not-
George Allaire was terrified of these in Yarmouth. he had a special study done on these things that he was terrified of having. He was glad it was voted down, frankly.
That's not who you talk to. You talk to people who are running them and find out what their experience
The
has been
reason
for
he
the
was
last 20 years.
afraid of it was because he had talked to people who were running it. We can do that. We can certainly do that. And it's, these things, like anything, are something that work in certain applications, and they will be looked at in this context. There's right places for them. That they're applicable in certain applications. It's not all or nothing. So
These are just.
Paul, you just have to wait, because other people want to speak. Yes.
Where do the solids go? And do they settle out? Do they have to get pumped? Where
Yes,
do the
they would still
solids?
sell out in your septic tank,
Where
and
do
you
they
still
go?
need to get that pumped periodically. Theoretically, depending on how it's designed, you could adjust the frequency of how you're pumping it out, because you're not as concerned about the water quality leaving it from, it's not going to a leach field anymore.
So it still gets pumped out somewhere.
Like a septic haulage would come and pump your septic tank out just like it normally would, and you just have to make sure that your solid buildup isn't interfering with the pump you've selected or the operating range that you need.
Do either the low pressure and the step stag systems require or at least recommend the installation of low volume flush toilets? Does that help in any way as a cost measure?
I would say that it would help in that it would help conserve capacity.
Right, but it's not a requirement of the system.
I know that, I don't know, I think that Bailey's Path in Chatham has a step steg, and I believe that the folks that use that are very satisfied with it, and they have found that it performs very well. I know the folks in Olympia, Washington have extensive step steg. Now, they started out with a traditional gravity system. They later, in order to develop outlying areas, switched to step steg to have some of these further out areas. As of a few years ago, 90% of their maintenance costs came from 10% of their infrastructure. All of it was step steg. Their gravity systems had virtually zero maintenance. I mean, it's expensive to put in the ground, but you put it in and it works. It runs, it doesn't plug, it doesn't have problems. The step steg, they said they had reduced their operating costs once they put in preventive maintenance of getting in and changing filters and changing pumps and doing a lot of that. But it was still extraordinarily high maintenance costs on the step steg. So they proceeded to pull out every single step steg system in the town and switch the whole thing over to gravity after a certain number of years.
As a frame of reference, the operating maintenance budget for Gloucester is $500,000 a year for their step system alone.
How many connections?
Well, about $1,250.
just a quick comment. George Allaire, about 3 years ago, asked me to do some research on this, and I did. I put together a list of do's and don'ts on pressure systems. And I'll send that to Stacy, and she can send it to everyone here. The issue is they work very, very well, and they're very applicable in certain situations where they fit perfectly, but they have to be designed perfectly as well, operated perfectly, because they are complex systems. This is a relatively complex system. So you'll get good examples out there where they work, and they may be applicable to certain parts of Orleans based on pros and cons of gravity and other things. But by and large, you have to really be careful of the design and the operation. It's just, nothing fits everywhere.
To that point, Mike, one thing, so when you are planning one of these systems, you size all of the piping based on what's going to be coming into the system. There can be instances where if you hadn't planned a certain neighborhood being connected to that system, there may be hydraulic issues depending upon.
And what happens is people put them in, the vendor disappears, and the town comes in and then adds in this new neighborhood, and it doesn't work. So it needs to really be managed, design and operation. Sorry.
If I could just comment, Judith talked about a brand-new system, Bailey's Path, designed, built, installed, operates.
Small, I think.
Yeah, 15 dwelling units, maybe 12, something like that. When we looked at this 2 years ago, extensively, I remember there were two issues that came up. And the engineers had two big qualifications. First, we can't tell you the condition of the septic tanks in the neighborhood that we're going to be doing this. And therefore, if I remember, you needed to have a 1,500-gallon tank, right? And it had to be partitioned half and half. And we didn't have that information. And second, there was a whole issue about horizontal directional drilling, whether we could do it or not. And those were the two items that the engineers said are contingencies in our estimate because we don't have the answers. Now, we are now in the process of trying to understand where the pipes are in the streets in a significant portion of Orleans. And Mike, are we also looking at the septic systems? I know we're, what are we doing?
We're looking at the detail at the septic systems in the downtown in order to look at cluster systems there, what's required for there. We're not looking at the septic systems individually in the rest of the town, although the health department has very good records on those. And they can tell us the size of the tank, the age of the tank, problems, et cetera, et cetera. So there's a good database there.
Okay, so my memory is that in the area that had been looked at 2 years ago, approximately 50% of the installed septic tanks might qualify for a step-steg conversion. The remaining cesspools and undersized septic tanks would not. So as we begin to look at this, we need to understand specifically what we're dealing with, and the data is
then
available.
even of those that would theoretically qualify, the condition, once they go in there, is also a factor too. Because, as Lou pointed out, you're basically taking out a piece of the top. You've got to do some destructive design and construction in those tanks to get this equipment to fit in. So again, they are a good technology. They're applicable, but in targeted, very directed areas.
Okay, so as we move ahead and we think about finance, the question is, who pays for the new septic tanks and pumps and connections in this system?
And another cost question, to the extent that you stop using the leaching field in your yard, does that have to be torn out, or can it just be abandoned entirely?
I believe they can be just
Abandoned.
Filled.
Okay, so all of this is informational. We're not at a stage to suggest one of these collection system components over another. So this is really just food for thought as we go forward. And your input is helpful, so we will try to find more examples and information for people who want that as we get to that stage. So should we go to PRBs?
Oh, I'm sorry, yeah, these pump stations, just another tool in the toolbox. We don't need to spend a lot of time on this. At some point, if you have to collect wastewater and get it to another location, sometimes topography is a hurdle. You throw in a pump station to get you from point A to point B. There are some O&M costs and some capital costs associated with these facilities. They would need emergency backup power for 100% of the time for any power outage. They can be designed so that they can blend in with the surroundings, and maybe you wouldn't necessarily know there was a pump station there. That drives up costs. I guess what you try to do is you try to minimize the number of pump stations to achieve your goal, because more pump stations just means more cost. Force mains, so anytime you got to pump wastewater, you have a force main. So it's just a pipe, certain feet of cover, make sure it doesn't freeze, and air release valves where there's high points where gas could collect. You need to make sure that it doesn't bind up your pumping operation, but that's about it. So no need to spend a lot of time on that unless there's specific questions regarding that.
Pump stations and force mains will apply to the effluent from any plant as
Right.
well, any cluster plant.
Good.
So we're going to move right on to a discussion of PRBs, and again, I'd like to introduce Angus McGrath.
Hi. As I was saying to some people, although I hail from Walnut Creek in California, currently my father grew up in Caden-Aram, lived around here, so I spent a lot of time on the Cape myself. So I don't consider myself a local. I wouldn't go that far, but I certainly understand the area. So, my background is I'm what Stantec calls a subject matter expert. My expertise is in situ remediation. I'm an environmental geochemist. I deal with soil and aquatic chemistry. I have a degree from Berkeley. I worked as a postdoc at Lawrence Berkeley National Lab studying environmental systems. And so if you have chemistry questions, that's what all of the Stantec folks look to me to answer. I can certainly try to help. Just diving in directly into the discussion about PRBs, someone had mentioned that there was a concern about the different types of PRBs, and that the perception is that the injection PRBs are injecting chemicals, whereas the trench PRBs may have more naturally occurring materials that are being put into the PRBs. I kind of want to dispel that impression because a trench and a well are merely a vehicle for getting the reagent into the groundwater. And in both cases, we would be using either natural products or food-grade reagents to do this. So there should be no difference in the chemistry. To add to that, in California, we have this burden of trying to keep salts out of anything we add. But whenever you're near the ocean, that concern really is no longer applicable. There is no way we can put as much salt in that water as comes in that salt wedge that's right underneath your PRB. So here, obviously, we would try to limit any additions that might impact water quality that way. But the reality is most of the reagents, all of the reagents we would consider using for something like this, and that we use for remediation are food-grade additives like soybean oil or ethyl acetate, which acetate sounds awful, but it's actually acetic acid without the hydroxyl group, or without the hydrogen on it. The ethyl portion of it is I guess the answer here is these are compounds that are totally biodegradable. They disappear into CO2 and, sometimes some organic acids that then get biodegraded themselves, like acetic acid. So whereas I talk about these things and they have chemical names, they are all natural products. They're all found in your environment and are not foreign to the environment. So let's dive into the actual types of PRB that we're talking about. And again, we're talking about permeable reactive barriers. These are a construct by which we can treat groundwater that flows through much in the way it's shown in this little figure here. I realize this is small. We'll look at it in a larger scale. But essentially, water will flow through this zone, which we're calling the reactive barrier. That barrier is permeable, and it tends to match the permeability or exceed the permeability of the surrounding soil, so that you have a more transmissive, as we like to call it. And that means the water will flow through more easily through that. Trench PRBs, where you cut a trench, literally, and then insert the reactive material or insert an inert material that you will then apply a reactive material to, these trenches are best for shallow installations, similar to the conditions you have here. Okay? What tends to happen is your nitrate is in your fresh water. The salt wedge comes in beneath it, and so you don't want your trench to extend into that salt wedge because it's a different quality of water, and it will consume your the reactive material that's there to clean up the water. So you install them so that there's this separation between the two, and the density of the salt keeps that fresh water flowing through your barrier. So this salt density differentiation with fresh water and salt water is actually a good preventer of the nitrate from then getting up, going around the barrier. So just some typical engineering things. The nice part about the trench PRB is that you can optimize the permeability of the area you're putting in the treatment so that you have some control or understand a little bit better how that will react. And then you can completely bisect the groundwater plume in the full extent. Right? Wells, as you can imagine, don't completely bisect it, but they influence the area around them, and we call that a radius around them. Well, with a trench, you're completely bisecting the flow zone. So that makes a big difference as well. And again, treatment tends to be more uniform across that trench because the material, the reactive material, is all the way across the trench. Now, one of the potential concerns that you can run into with a trench PRB is that, in some less permeable areas, you might change the permeability by scraping the sides of the excavation. Well, fortunately, in Orleans, you have a good deal of sand, and you can't change sand very much to change that permeability. So the good part about the area we're looking at is it's optimal for these kinds of applications, be it a trench or a well PRB. And so jumping to the well PRB, it gives you a little bit more flexibility. As you can imagine, if you have utility corridors coming through an area where you want to do a trench, it's hard to cut a trench around a sewer line. You can do it. It happens quite a bit. But these complicate the application. You have electrical lines that are running underground or whatever. Those can complicate the logistics of doing this. Whereas wells tend to have less of these limitations. So you can put wells in a series, in a sequence, much in the same way that trench is there, you'd have a series of wells. Obviously, a trench has a depth limitation. You can't put a trench extremely deep. Fortunately here, we don't need that flexibility, but the well PRBs give you that flexibility. And then, to a certain extent, well PRBs give you a little bit more treatment flexibility. If you put the reactive material in the ground and you decide you don't want this technology, you have to take that back out. If you use wells, then you just stop putting the treatment in, and eventually it dissipates. So those are some changes that apply to this. Typically, we don't just put a PRB in and not have any other components added to it. We do what we call a hybrid system, where you install a trench, but you put some piping in to allow you to control flow and, if needed, inject additional substrate for treatment and so forth. So the hybrid PRB gives you that flexibility that you have in a well PRB. And in some cases, you might not even, as I mentioned initially, when you do this hybrid trench, you could put in inert material that just allows you to distribute more evenly. I will say this about our area here, is that with as good a sand as I'm told you have, that a hybrid PRB is not going to be very different from a well PRB in that respect, because the wells will have a good radius of influence in that sand. So those are just some discussions. To give you a visual of this, we just constructed a cross-section. This would be the reactive PRB that you have. This is the nitrate plume in the groundwater, and you can see we've designed what we call the overburden, the soil above the groundwater here. And then, although this is blue, obviously it's not a subterranean lake or river. It's actually sand with groundwater in it. And then the groundwater is flowing towards the surface water here, So you have your nitrate plume. It comes in contact with this PRB. Depending on the rate of flow, it then gets treated, and then there may be some metals like iron and manganese, depending on how it's designed, that generate locally to the barrier, and then as that water gets oxygenated, that goes away and it comes out. Okay? So the design here is critical to making sure that you don't have what we call the adverse effects that come into that. Just to give you a picture of how this is done, this is a large trenching machine, not too dissimilar from the little ones you've seen people use that looks like a chainsaw blade that they cut trenches with. Well, this one's about 20 feet long. So, and then it has an added feature, which is this trough here, which allows you to dump the reactive agent or filling material right into the trench as you go. So this is what we'd call a one-pass system. As you can see, they have no shoring. And what I mean by shoring is boards or steel plates to hold that side back. In sand, you don't have that option. You need big, large, strong steel plates to hold back the tide of sand that's going to fill that hole while you put in the material you want to work with. And so here they just use an excavator and use these plates to control it. And you can see this is approximately the depth that you do here in Orleans, so it's about 20 feet, and that's typically done and not unusual. For a well permeable reactive barrier, we have a similar construct. And you were saying that in this case, we have the wells in line. So you can see one is taller than the other and so forth as it goes over this hill. But essentially, there are a number of wells. And actually, I think you have that little video. Yes, here we go. Let's just jump to this very quickly. And this gives you a nice three-dimensional view of how it looks. So you can see that, from both directions what those wells, and that's a generic view of what we're talking about.
Judy, did you have a question?
Regarding capture, since those wells are next to each other, I mean, how much goes in between them and is not treated?
That's a good question. So what we do is we design the injection wells to have a certain radius of influence. So, and I'll discuss this more, but one of the big initial parts of the work that you need to do is do some testing of your aquifer, because it's totally site-specific, to see what the permeability is and what the expected radius around a well is for the amount of solution that you would want to treat with.
You overlap the radii, or so that
You tend to. It really, the design is based on how efficient you want this system to be. So if you're, as you're suggesting, if you want this to be, 100% or more effective, then you would overlap the radii. And sometimes we do that by, rather than putting them all in a well, staggering, having one set of wells here and another set of wells there, and they're offset by half a radius.
Okay.
And that way, it fills the gap in the same way. Okay? It's a great question.
Thank you.
Thank you for bringing that up. So as you see, in the same way, the groundwater flows through here. The wells, as she was alluding to, have this radius of influence. That radius of influence generates the treatment and then allows us to do the remediation. One of the things I want to make clear is that nitrate is one of the easiest, geochemically, if you're going to what we call anaerobic conditions, so lack of oxygen, the first thing to go is oxygen. The next thing to go is nitrogen in that reductive process. So nitrogen is used once oxygen is gone. For adverse effects, and I'll show you this, you go to more reducing conditions. So if you can stay in that just deoxygenated zone, you have the ability to treat your nitrate without generating other things like iron and sulfide, which were seen at some of the other test sites, and we can talk about how that was problematic because of how they applied it. Just a perspective on what it looks like. This is actually a nitrate pilot study injection, and here are the injection wells we did, and gives you an idea of, if you were going to have it show up at the surface, what it would look like. Typically, these wells, we plumb them so that you don't even see the plumbing locations. I have an industrial facility where they operate forklifts all over the wells, and there's nothing to get in their way. There's just these metal vaults so we can get into the wells and check to make sure that things are happening properly. Here's a site in Indiana where we've put in a number of injection wells to be a barrier to flow in a...
So what are the black silo structures in that?
So these are tanks that we use to mix up the solution.
The goo and stuff?
Yeah, in our case, because this is a chlorinated solvent plume that we're treating, we're adding carbon more frequently than you would, for instance.
And the scale on this to go to the, I see the pipes or the hosing that connects, so what's the scale?
So,
It looks like a utility pole, so the utility pole is what, 8
that's
to
about
12?
100 feet away.
Okay, thank you.
Yeah, I was trying to calculate it out by the number of wells. It's somewhere around 100 feet, and and as I said, these are we don't always leave tanks out there. In this case, we have the luxury. This site is not used for anything at the
It's an
current.
industrial site too, in a way.
It was at one time, and it's been in cleanup.
Sims.
Understanding that
Sorry.
wells can go pretty much anywhere in terms of how deep you run them. This question of, I guess, applies mostly to the trench, but to a certain degree the well. Where is the nitrate likely to be in the groundwater flow? Does it stratify at the top? If you're only going down into the groundwater flow a little bit, are you pretty sure you're getting the lion's share of it? If it is a very tall groundwater stream, how do you capture a reasonable amount of the nitrogen? Understand that this would be a limiting factor with trenches, but how do you figure out where to put the medium in when you're using wells?
So that's a great question. When you're injecting with wells, you pretty much want to, in all cases, want to inject across the entire interval that you're trying to treat. So there can be stratification of nitrogen. Typically with the low concentrations that we see here, you don't see as much stratification. But there will be some no matter what. And so part of the initial investigation when you're doing the feasibility testing or we call it a feasibility study, when you're looking at the site, evaluating the site-specific requirements for doing this work, we then go out and we look at what is the depth discrete concentration of nitrate or whatever chemical of interest, we call it. And so we will then do depth discrete sampling. If you only have a 20-foot zone, that may only be 3 samples taken. And then from there, we would look at also what is the fluctuation in the water table to know how far across to screen the well to do this. If we find stratification where their concentration's different, then we would potentially screen wells at the bottom or the top of this and have separate screens for each of those wells. And when I say screen, I call it a screened interval. That's the permeable portion of the well. Obviously, parts of this well is a solid pipe, so only parts of the well are screened. Typically, for a treatment zone, we screen up above the water table to make sure that we can accommodate fluctuations in the water table. Now, another point is that some of our treatment reagents float a little bit. And so, for instance, emulsified vegetable oil can have a tendency to float. So you would inject it at the bottom, and then it will tend to rise up and cover the whole area. And so these are very good things to understand before you implement. And I should say, this is typical of every application. You need to understand your aquifer before you start treating it, obviously. And a big part of that is knowing the width of the plume as well.
Angus, some of the applications you're referring to are obviously, they're toxic contaminants,
Right.
Chlorinated solvents and stuff like that, where you have to get virtually 100%. In our case, we're talking about nitrogen plumes, where we could be talking about 50% reduction, or 70%, or 80%. So that would change a little bit your conservativeness in terms of covering the float at the top, or your spacing, or like
Exactly.
in one case I saw, because of utility constrictions in the ground, a trench was actually put here with another 150-foot gap and then picked up again. And it still caught the 60% necessary. So you have flexibility here that you might not have in other applications.
That's a great point. So what we typically do is look at a mass flux of what's going through. And that mass flux would then say, okay, what do we want? And we use the term receptor, the endpoint. So what do we want the reduction to be at the receptors? And then we calculate how much treatment we might need. And we tend to be a little conservative. And then the nice part about injection wells is you can back off if that's too conservative and reduce the costs in that way. So just to give you a couple of quick case studies, we've done a lot of permeable reactive barriers. This is a trench application where we use zero valent iron and sand in this. Now the benefit of the zero valent iron is the iron reacts and it generates a reducing condition by itself. And then the bacteria take that reducing condition and they generate a good anaerobic bioreactor, which is actually extremely effective at removing nitrate. Our target chemicals were different in this case, but we can look at nitrate removal based on the efficiency of the VOC, the treatment, other compounds of concern here. So this was a 200-foot long by 2-foot wide by 20-foot deep trench where that's operated for 15 years. There have been no plugging issues with this and no loss of performance over time. Now, one of the things about these iron barriers is they're also very effective with phosphate, if that is a concern. The iron barriers tend to generate some more adverse effects. They have iron they put iron into solution, and so you need a buffer zone, a larger buffer zone to adequately use this. But yeah.
Just to get the metrics, how much did this cost to design, install, pilot, and so forth in the ground and ready to
We'll get to that. We'll
yeah,
get to cost.
yeah. I mean, costs. I couldn't tell you. This was done 15 years ago, so I don't have access to those numbers. But yeah, we can talk about some cost information.
Yes.
If you're injecting a liquid, wouldn't that cause its own plume and start to travel with the groundwater?
That's a good point. So what you want to try to use are compounds that don't tend to travel. And so one of the attractive things about emulsified vegetable oil is it's emulsified so it's in little droplets in the solution. And those move only a certain extent, and then they basically, they don't absorb, they just coat the soil, the sands around it. And so that gets trapped then, but continues to feed microbes. So, yeah.
Who tracks it, and what are the costs involved with annually tracking what's going on? Because this looks like it's pretty non-costly.
Do we get into that?
Yeah,
Okay.
we'll
Yeah,
get
I
to
mean,
costs.
so typically your monitoring costs are are higher to begin with when you're proving the technology, and then decrease over time. So that's about all I can say.
I was just going to build off it. It's my understanding it's all natural. It's not chemicals we're putting into the ground, but it's not naturally there. Are there any negative impacts? I mean, anytime you're playing with hydrology,
Right, and I don't want to try to sugarcoat it. As a friend of mine says, there's no geochemical free lunch. Right? So if you change something, you're going to change something else, right? And so as you turn the system anaerobic, and I have a slide that sort of is a primer on what happens when you go anaerobic, and we'll get there.
Okay.
All right, so let's quickly jump. Oh yeah, sorry.
Okay, so just quickly follow up to what Chris was saying. I was sitting there as we were talking about how it's all natural, and I'm sitting there thinking, yeah, arsenic is too. Doesn't mean that we want to put it into our groundwater. So I would assume that any test site that we would be looking at, we would absolutely eliminate anything that was upgradient of a drinking water supply, since we don't know how much this stuff's going to travel and what the effect might be. But I'd also be very concerned about those things that are near our salt ponds. I think we're looking at one near Lonnie's, for instance. That's our herring run. Can we be certain that the vegetable oil is not going to travel into Lonnie's pond or travel in any way to negatively impact our herring? Or if it's trench and we're talking about wood chips, I mean, I know Sia has said that the problem there in Falmouth was that it was too close.
Two slides to talk specifically
Then I'll
about
be
it.
quiet.
I think
Carry
we
on.
should
Thank
get
you.
through the presentation.
Yeah,
'cause we
we'll
can
get there.
Try to address all the stuff that I know
Okay.
you're going to ask.
Thank you.
So here's a case where we used did a well PRB. We used emulsified vegetable oil. We actually inoculate this with microbes to get the reactions we want. It's 100 feet long, 45 feet deep in this case, 20-foot diameter. I can speak endlessly on this. This is something that I've been doing for years. This was 98% or more efficient for treating nitrate. So in this case, we had some nitrate on site. We monitor it. In California, there are very strict requirements on what are the byproducts that are generated. So they're asking us to look at arsenic and other things as well. And so that's part of the mandate in terms of discussions here. In this site, we didn't see any adverse downgradient effects, but we did see a significant decline in nitrate to non-detect values. Now, if we went to slightly lower detection limits, we'd obviously probably find a trace amount of nitrate, but this was very, very low. And although we didn't test it in this case, it also has the potential to treat phosphate. Okay. So those are two examples. These are just examples of other PRBs we've done. They vary in composition and what they're treating, but this is a well-known technology. We've done a lot of PRBs, predominantly well, but that's mostly comes to the issue of we're doing them for temporary purposes, not long, extremely long-term applications. So that's part of it. We've also done a lot of feasibility testing on these sawdust wood chip barriers. We've got one under implementation. The only reason I don't have nitrate data for those is we typically apply those for hydrocarbons. And when you have hydrocarbons, you don't have any nitrate. The hydrocarbons take care of the nitrate. So unfortunately, that's part of the decision. So getting back to your question now. So Wacoit and Childs River pilot studies looked at a wood chip biobarrier, permeable reactive barrier. They used what's a Nitrex PRB. I asked Sia to send me information on exactly what a Nitrex PRB was so that I could answer these questions. It's essentially lime and wood chips, so that part doesn't change. But their results were a little mixed, but they decreased the nitrate substantially. Part of the problem was some underflow, I gather, at the Childs River. But a big problem with the overall design was where that barrier was placed. The barrier was placed near the beach. So for me, number one, hydraulically, that's a big no-no for when we do the applications, because you want consistent water flow through your barrier. If you have variations, tidal fluctuations, then that creates a problem. So you want to be as far back as you can and still be protective of the watershed, but also you want to make sure that you have as consistent a flow as you can as well. So first you'd want to do a hydrology study just to take wells and measure the gradient, right? So that's a typical application of any kind of work you would do for this. You go out, you measure the gradients, and you see how they change during the day. That can be done in a month, so it's a simple resolution to that. The other was that they saw some ferrous iron that then oxidized on the beach, and I don't know if you've seen pictures of it or whatever, but it did show sort of a brown staining on the beach, and that's a result of some iron that got dissolved as a result of the reductive process. This is a very sandy formation. Most of it, I would assume, is pretty high in silica, but it's still going to have a little bit of iron in there. And so that can create a little bit of iron getting into the water, and as well as a little bit of manganese, which that'll get into the water as well. So if you just separate, you add a little bit more space between that barrier and the beach, then that iron reprecipitates in the groundwater and never makes it to the beach. Okay. Also, there was a salt wedge issue with the salt getting into the trench. The microbes tend to like to take sulfate and reduce it under reducing conditions. They breathe it, essentially, and so the sulfate-reducing bacteria generate sulfide. And again, sulfide is not something that, particularly for us when we deal with water quality issues, they ask you, okay, what's a safe level of sulfide that you can discharge to drinking water? And the answer is always 0, to which I say, okay, then we got to make sure we have plenty of mixing. And the way we would do this, we would avoid going to sulfate-reducing conditions as much as possible, and that's very possible. You're going to have sulfate in the water at a certain level. You just don't want those high concentrations that are in the seawater. The other side is that you could generate some methylmercury. These sulfate-reducing bacteria can methylate mercury. Well, it turns out that they actually did look at that at the Childs River and Wacoit sites, and there's virtually no mercury in the sediments or the soils, and as a result, there was no mercury being mobilized as part of this. And my understanding is the same is true for arsenic. So arsenic, as you mentioned, is a naturally occurring element, like most of these, but the concentrations are low. It can be dissolved out, typically in clayey soils where there's a lot of iron and other things. And we deal with that, unfortunately, in California a lot. So the solutions to the problems here are really location. Install the barrier further away from the beachfront where you have a little buffer zone to reoxygenate that water. And second, to make sure that you design your barrier so that you're away from the saltwater intrusion wedge. And you can do that in several ways. One is, if you have a trench, to put an impermeable layer at the bottom that blocks the wedge and keeps it from coming into your trench. It prevents underflow so that water that's contaminated doesn't go under your trench, and it forces the water to go through, but it keeps the fresh water separate from the salt water. So I realize that it may not be easy to visualize these, but the simple answer is there are solutions to this. 1 second, I'm almost done. So just part of the discussion for the Wacoit Childs is that they went to generate iron. Okay, so let's talk about what we're looking at here. Ignore the, this, I use this slide for contaminant chemistry too. So this is your local gas station plume, right, generating this. But it's instructive for our understanding of what's going on geochemically. When we have oxygenated water, we have just your typical anions and cations. These are the salts and minerals in the water. What happens as we get to more reducing conditions, so after we deoxygenate the water, then the microbes start taking the nitrogen, the nitrate, and turning that into nitrogen gas. Okay? So that's that first step after deoxygenation. Then what happens is as you get more reducing, then manganese starts coming out of solution, then iron, and then they start reducing sulfate, and then you actually go to where they will generate methane from the CO2 in the water. So you have to add a lot of carbon to get to this range here. You can add a very small amount and maintain these conditions. And this has been studied pretty well for treatment of perchlorate, a contaminant that we have a big problem with in the West. So it's not an unusual application to dose this carefully. We're involved with a big project that has hexavalent chromium where they don't want us to generate manganese. And so, for the water quality issues. So these are problems that have been surmounted. They've been done, and the questions have been answered. Okay. But just generally, then, let's just talk about implementation. How would you do this? So it begins with, as I described, a site characterization. That's where you go out and you evaluate the hydrogeology to know how the water's flowing. You look at the dimensions of the plume, so you know how, where the nitrate's present, how you could bisect it the best. And from that, you're going to design your permeable reactive barrier, be it a trench, be it wells. And then, obviously, you're going to have the installation of that barrier, which is essentially an infrastructure project. When you designed your home and put in that septic system, well, essentially, we're doing the reverse here. We're putting an antiseptic system in for you. And then there will be some operation, performance monitoring and maintenance that goes on with this. And it really depends on the type of barrier that's selected as to, how those costs might change. With that, I think I'm handing it over to you.
Sure. A couple of brief things about Falmouth. I'm going to leave time so you can talk about Angus more when you get to see me again.
Just hold questions for a minute. Let's just get through this and then.
Very briefly. So Falmouth did a feasibility study. We had a consulting firm come in, and we did some work to understand the basics of PRBs. One is they did a literature review to understand the existing knowledge base. A big concern for Falmouth was what was going to be required of permitting, and so we have a very good, I would call it the handbook of permitting for a PRB. It's in a tech memo that's available. It's a public document. And I summarized that in the tech memo that I provided to you, a bulleted list of what the permitting agencies are. They are permittable. When we had working groups in Falmouth, we had regulatory bodies sitting at the table, so we started to understand practically what it would take to permit a PRB. We were at the CDM, who was the consulting firm, was asked to look at these down gradient, and their recommendation was a 100-foot buffer, and you should cover, you should not have your receptor within 100 feet so that you had any impacts. We created a screening matrix to identify locations in Falmouth. Started to look at what did the studies from other places tell us about what the efficacy of nitrogen removal was. We have another document that talks about performance monitoring and what's going to have to be done. In fact, there's a monitoring committee meeting of the Cape Cod Commission that's going to be looking at what is going to be required, or what is recommended for monitoring, which is another piece of this for Falmouth. And then we had some preliminary cost estimates done. And so what we found is, given a siting matrix and all the other considerations that you'd want to take into consideration, road layouts were the best place to put PRBs. I mean, Took a lot of time to figure that out, but road layouts make a lot of sense. And a 100-foot buffer. In Falmouth, trenches were not feasible because, as Angus was saying, you want to intersect the entire, what I call the thickness of the aquifer. You want to get to groundwater from the surface, so there's a depth to groundwater. Then you want to do the thickness of the aquifer, and in Falmouth we were looking at over 40 feet. And so given that and the roads that we had to work with, trenches weren't going to work. So that was a big finding for this almost one-year effort, is there aren't many places for trenches in Falmouth that make sense and have the buffers, et cetera, et cetera. So we then began to look at wells and found that there were some places where wells made sense. And right now what Falmouth is doing that feasibility work that Angus was talking about. We're looking at, how's the groundwater flowing? What is the gradient of nitrate? Is there concentration at the bottom, at the top? We've got USGS looking at it as well. For our fingers, our seacoast shores, if you know Falmouth seacoast shores and the Great Pond area, so we've got these fingers on our south coast. And the cost information that we got is and I studied it. There are tables, there are tech memos. I know Orleans, I certainly know Falmouth. And it's not a good, the cost numbers are not comparable because the trenches were so deep that they were very expensive. So the trench numbers for Falmouth, I think, are too high for what we'd be doing here in Orleans. And the injection well average capital costs are also very high because of the depth. 80 feet. West Falmouth Harbor was an 80-foot well. That's not what we're looking at here, so I don't want to talk about numbers. These numbers are very high for what we'd be doing here. And then last but not least, I promised when I first started in Orleans that I would really leave no stone unturned in looking at alternatives. And I really have tried to do that. And one of the things that I did is, although we've had 2 literature reviews done for PRBs, I did another one. And I found a few very important installations that hadn't been turned up yet. And this is a list of them. Brookhaven, New York is right now putting in a PRB to look at remediating their nitrogen plume. They have septic. Long Island is a lot like Cape Cod. It's got a lot of septic systems and sand. So they're looking to remediate nitrogen going into Ford River. So I'm in conversations with them right now about what their feasibility study was, depths, all that kind of stuff. Pinter and Associates, which is a Canadian firm, put in a trench PRB specifically for nitrate removal at a factory. It's been operating for a few years. What they were able to see already is that in the trench, the nitrate has been removed, and now they're waiting to see downgradient impacts because it's clay. Schmidt is a recent publication that has used trenches to remediate nitrates, specifically for nitrate removal in groundwater. Nuttall in Arizona, New Mexico, actually put a ring of PRB injection wells around a groundwater well, water supply well. They are specifically remediating nitrates to keep it from going into groundwater. So that's another successful application. And the Robertson and the Shipper papers are, in my opinion, the oft-cited foundational research papers that prove out 2 things. One is longevity, over 15 years, and establishing that it is denitrification that is the cause of the nitrogen removal, which I think is very important. If you're just taking nitrogen and you're turning it into ammonia or something, you're not really helping your estuaries. So the idea that denitrification is the turning of nitrates into gas is very important, and not turning it into methane, for example. And then the Schroeder is the documentation of a pilot installation for nitrate treatment of another injection well installation. And so this is just to show there are actual projects. Orleans would not be the first, and we do have data that shows that they work, and you can mitigate, as Angus talked about, the downstream impacts.
I can just say Dave Schroeder is a colleague of ours. Technically, I guess, on the subject matter expert line, he reports to me, but I consider us equals. Okay, so what do we have? Yes.
Regarding your earlier slide, it looks like the nitrogen reduction was 99%.
Sure. In here, it was very high. Yeah.
Okay. one thing you didn't mention is this treats all the nitrogen in the groundwater, not just from septic systems, whatever nitrogen in the nitrate form that's going through the water.
Yeah, so,
So you get
Sorry, go ahead.
a ratio higher than 1 in terms of nitrogen reduced compared to septic systems. Is that correct?
yeah, I think that's a fair account. Essentially, we have, in this case, you know, there are no septic systems in this area
No, but-
anymore. But essentially, you know, the fertilizer or whatever nitrate that was there was treated.
Right.
And I would just add to that, what that speaks to is how you would calculate load,
Right.
the load that you're treating. And in our case, we look at not just the septic watershed load, we look at all the others.
Okay. I'm still frustrated that we can't get order of magnitude costs from any of you people because in the sense of Falmouth, whatever those costs are would be the high end. And, you know, this is just important to get a sense of how this compares with floating islands or septic, you know, sewage systems or anything. One last
Well,
comment.
he's going to answer the cost question.
Sorry?
Just quickly on the cost. I mean, you know, I guess my answer to that is that cost depends on a lot of site-specific things. So an order of magnitude cost for one area is different for an order of magnitude cost for another. And I, you know, I think we're getting there on some costs. It really, you know, you have to kind of start slowly, get to know the system, and then generate those things.
I've done hundreds of Superfund sites in the upper levels of cost analysis, and I've looked at cost versus length and depth and so forth and gotten calculations. One last thing, the last slide that Sia put up, can we get either the websites or something so we can?
I will give you the citations. I just wrote those up. I will I have all the paper names. I'm going to have them here if you want them, but I was going to write out the actual names of the paper.
Go to Stacy and then to all of us?
Yep.
Thank you very much.
Will do. Other questions? Thank you.
Talking about phosphorus removal, it moves in a different way. It doesn't move with the groundwater. Of course, it moves by binding to particles of iron. I think iron is prominent among those. So we have a longevity of 15 years for nitrogen removal. How quickly or how slowly would all the particles be bound to what's in that trench?
You know, I think it's hard for me to speculate on that. I mean, I think, as you pointed out, part of the problem, you know, typically when I'm doing in situ treatment systems, I don't worry about phosphorus because it doesn't move for all intents and purposes. Here in this sand aquifer, it has the potential to move with particles. So there is that issue. I can't speak to it in Orleans without some analysis of the water to know whether phosphate migration is a major issue, and then speculate on how well it's going to bind. You know, I'm just off the top of my head. It's not really anything.
There is one, just to comment on that. There is a good application for phosphorus on the Cape. I mentioned before at Schumann Pond on Joint Base Cape Cod. I think it's been operating about 15 years. It is a phosphorus PRB. It's been successful. They've done a lot of monitoring, and it's worked. Of course, it's on a private government installation and everything, so it didn't have the issues there. The issue with phosphorus, having dealt with it on discharges, is that it takes a while to build up. Whereas as nitrogen starts to move, there's a saturation point with phosphorus that you know better than Angus. There's a saturation point which it has to hit before it starts to move, and that's different for different.
Right, and because this is a sandy aquifer, your saturation point is pretty low. Your absorption sites are not that many. So where we are on that saturation curve.
Okay, so I have Josh, Alan, Judy, just mindful of time.
Two things. Can we see, following on this slide, some examples of unsuccessful applications so we could understand some of the risks related to our situation.
Well, Coit is a very good unsuccessful.
You know, and I think it's important to kind of temper what does unsuccessful mean. In the case of LaCoit, it was pretty successful getting rid of the nitrate. I think we'd all agree that you'd prefer not to have the iron forming. I'm not a biologist. I would say that potentially having that small amount of iron generated is not as harmful to the ecosystem as the nitrate. But I'd rather not have those trade-offs at all.
And try to be a little delicate about how I say this, but I just want it to be transparent that Stantec manufactures and installs these and has a financial interest in the installation of PRBs, and is also consulting on it with us. So just,
So I don't know of us manufacturing any of these.
well, okay. Stantec PRB projects, that's not,
So no, these are this is something that I should make clear.
Right.
Is I take a point of interest in making sure that I don't have a financial leg in any of these things when I talk to you. And if I do, I try to let you know right away.
Okay.
As far as I know, we don't have any PRB technologies. There may be some wetland applications where the guys have applied for patents for different. So in that case, they're what we call biological engineering systems. But even there, I don't know that we enforce patents or try to sell products at all. And that's definitely true. We're a consulting firm.
Alan, sorry, Alan,
Sorry,
Alan,
Angus,
Judy, and then,
You used a couple of terms that piqued my interest. You need to know the width of the plume, you said at one point, and then you talked about the dimension of the plume, and then you talked about the Finger Lakes laundry, which was site-specific. You talked about your case in Palo Alto, which I believe was site-specific, and SIA has given us Pinter and Associates removal of a plume from a fertilizer factory. How do you relate that to a town that has miles and miles of water front, and the average lot size is an acre or 3/4 of an acre, and they are spread all over? How would you then decide the size and the location of a plume if you were dealing with a water body?
So, I mean, so the EPA has gone to a TMDL, which is basically a mass loading and daily load to a water body evaluation. And so when we typically look at the potential exposure to a receptor group, we use a mass balance kind of analysis. And in that sense, you look at, for instance, if you have a pond or whatever water body, you evaluate how much of the flux of nitrate going in you would need to mitigate to treat that pond. And that is a feasibility analysis. You say, can we treat enough water to make this pond healthy, or can't we? And therefore, and then what's the cost-benefit analysis of that? And that is when we collectively come together and say, okay, here's what we can do. Here's what it's going to cost. Do you think that's worth achieving? And so from a perspective of, is this, if I'm going to go around putting Band-Aids on each cut here, I think that clearly source control is the top priority here, as much as you can, to keep that nitrate from getting into the water, and then mitigating the residuals that you have to deal with. And that's a good comprehensive plan for how to deal with it.
Okay, so each site has to be looked at extremely carefully, because each site is different.
And I would regionalize it, because obviously you're looking at mass flux into a larger area. So rather than look at individual homeowners, obviously you're looking at for instance, you would say, okay, what's the watershed for this? And you'd know the direction of water flow. And then you could say, okay, well, in this watershed, because we have constraints that we know that there's a catchment to a certain degree, then you can design barriers to that. Or you design to say, okay, well, we have this very large watershed, but most of the nitrate is only coming from this select area where there's a higher density of septic systems that are creating a problem. And so you build the barrier to take care of those, knowing that you probably have 40 years worth of flow that's still out there coming at you.
Okay, and then you look for a street, and then you look for 100 feet back from the watershed to see how those work.
Yeah, I mean, I think part of it would be a flow study to see what's the travel time. So 100 feet may be very conservative, because what tends to happen is as you get closer to that water body, your flow rates diminish. So whereas you might have a higher flow rate away from the water body, the water starts backing up, obviously, because it's now tidally influenced. And so the key, more than anything else, may be, can I get far enough back to eliminate as much as I can of the tidal influence so that I have good, consistent flow? I would bet you that you can't completely here because you're so close to the water. So then it's a matter of saying, okay, well, my average flow through here is relatively consistent in New York.
And then you write off all the waterfront property because they are right on the water.
Pretty much, yeah, unfortunately. Or you do what my dad did in Martha's Vineyard on the pond where he was. He has a Clivus toilet and a pump tank that gets pumped out.
Thank you very much.
Judy?
I know this is nutrient-driven, but I was curious, have these been used to treat pharmaceuticals, or can they be used for pharmaceutical treatment?
That's a good question. It depends on what the pharmaceutical compound is. I have a colleague who has done extensive testing on pharmaceutical treatment for drinking water and wastewater systems. So we have potentially an answer as to what types of systems could help with that. I'm not the exact person to answer those questions. And I should say that, like Dave Schroeder, who's on here, we have the nice part about Stantec is we have a lot of people who can bring you a knowledge base if there are questions. So I can tap into our subject matter experts and answer some of these questions.
Thank you.
Ed? Oh, good. Judy?
So back to Josh's comment about, where have things gone wrong. I think most of the people in town would agree that having our beaches turned red from iron is not minor, that is, in fact, a fairly major thing. But my understanding in Falmouth was, as well, it changed the pH of the water. All of the shellfish disappeared in front of that property.
Hadn't heard about that.
Maybe that's one of these rumors that's untrue. But I think we really want to be very certain that when we take care of one problem, we're not creating another. And so back to Josh's comment, I think it's very legitimate that we get full information on where these things have failed and what the downsides have been and what the negative consequences of doing something like this are.
I can't.
Yeah, I mean, it is, I look at how long these things have been up and running, and I think there were only 3 that were in excess of 10 years. Most of them are 2, 3, and 4 years. I don't know that in 2, 3, or 4 years we're going to see what kinds of problems come out of them. And I would hate to have the town spend millions of dollars to put in something only to find that it might have done a great job of taking care of nitrogen and gave us incredible additional problems that we now have to solve.
Right, and just to speak to this a little bit, so typically for our applications in California, and so we can take examples of PRBs in California. I wouldn't just limit it to what Stantec has done. I think there are lots of others that are out there that we can pull into this, but they have requirements. They call it a waste discharge permit, but essentially if you inject anything into groundwater, you then have to monitor the groundwater beyond a certain point from that treatment point. And they test for a full battery of contaminants and also just naturally occurring things, so metals and some organic compounds and so forth.
Yeah, these are very fragile ecosystems. So, you know, you start messing with them, and you change this a little, and you change that a little, and it's not like we're pouring huge pollutants into them, but suddenly we turn around and we find out that we've destroyed a resource that's very valuable to the town.
Yeah, I can't agree with you more, and I have to say, I don't want to be associated with something that damages part of an ecosystem I love. This is a great area.
Mike, and
I have a couple of questions, Angus.
Sure.
Maybe one's for Sia, but the comment was made that it became clear in Falmouth that siting in the streets was the best approach. And I can see why private landowners and others would force you to the streets for siting. But I'm interested in the other issues in the streets with regard to utilities and lateral connections and other things when you're digging up streets, regarding maintenance of the monitoring system, if it's in the street, O&M of the system if it's in the street, construction in the street, and the utilities.
Yeah, that was our siting matrix, not his.
That's
So,
what- yeah.
control, land controlling the property was the main reason. Distance, not putting them on beaches because you don't have enough of a buffer distance. We looked at the utility, people are constantly digging up streets and putting other things in. It's part of the installation that's hard. You just have to manage it, right? You turn the water off, turn the water back on.
Did the utilities, when reestablished, go through the barrier, or was it
Yeah.
discontinued?
Yeah, that was the idea.
TV won't pick it up.
Oh, I understand.
Or pass.
I don't
Pass
have
this
a microphone
Yeah.
there.
So the idea is to have your utility go through the barrier. And it's another reason to look at the injection as opposed to digging a trench. It's certainly easier. The monitoring is going to be upstream and downstream. So the monitoring system itself is mostly outside of where the actual trench is for performance monitoring.
So that would be on properties or people's properties.
Or in the right-of-way that isn't
Yeah,
paved.
okay.
You'd probably do it that way.
I guess the other question I have is for Brian. The other question I have, I should come around to hold that up.
The
I'll
TV
speak.
won't pick it up if you're not
It's a TV
speaking
issue.
into the mic. We hear you, but
Sorry.
the audience out there may not.
The other question I have is for Brian, and that is with regard to the permitting. The perspective on general and permitting these going forward for application in, for nitrate in Cape Waters, and has there been any permitted by DEP for nitrate on the Cape or in Massachusetts?
No, I don't believe that we've permitted any specifically for nitrate or for nitrogen reduction. What we would be looking to do, through demonstration projects, is to try and ascertain their effectiveness, their reliability, and then be able to assign some sort of nitrogen credit to them. And then with that nitrogen credit in place, then communities would be able to go ahead and use that number to integrate into an overall plan for how much they can expect to get, how much nitrogen reduction they can expect. But it's going to involve a lot of things like, evaluating what the exact, what the capture zone is, what the nitrogen load is coming into that, emanating from that capture zone, then how much will be eliminated as it passes through the PRB, and then factoring that all into an overall scenario to see if you're going to actually meet the targets.
And would it do you think, include MEPA and public input to the process?
Well, I think from the perspective that it's all part of an overall plan, that, that the community or communities would be developing either individually or jointly, as.
So it would
as
go
part
through
of
as
the
part of,
CWMP, yeah, that go through NEPA.
So, we're out of time. I want to make sure we have time for public comment, so we didn't allow public to comment during the meeting. Public comments. Anyone? Well,
Do you
that
have
means
anything,
your representative asked your questions for you.
do you have anything to say to close?
So what I want to say is, sorry we ran out of time and didn't get through
We're working hard.
everything. I do want to say that for the next meeting in 2 weeks, what we intend to do.
meeting on the 10th?
The meeting on the 10th, sorry, there was a change. So the meeting on the 10th is now on the 17th, but in the morning. There is on the 10th a meeting to discuss tracker. That's at the Cape Cod Commission. But the next panel meeting is on the 17th in the morning, starting at 8:30. Please hold until 3. We're not hopefully going to go till 3, but hold until 3 because we want to have that flexibility. We don't want to run out of time to get input on this initial plan so that we can move forward, refining it, etc. The intention is to do a brief presentation and then to really put you guys to work in small groups, evaluating, discussing what you like, what you don't like, how well you think this meets the criteria that we have set up, and then come back together and share that together. That's the general plan for the next meeting. So if we go longer than 12:30 or 1, we will plan to be bringing in lunch. We'll know that in advance. We'll get you an agenda out in advance, materials in advance as much as we can. And so come ready. Come ready for that.
I was wondering, in terms of the breakout sessions, what happens to those?
Yes. So we're gonna assign groups for the panel, and everyone else, the doors will be open. There'll be a little bit of standing room only in the breakout rooms, but you'll be welcome to go sit in on one, wander to different ones, as long as you're not interrupting, really just to sort of sit in and observe. Observe, exactly. Yes?
To add more problem to our discussions, do we have an appropriate time to talk about the CLF situation and what the implications?
Yeah. So I've been talking with the commission about that, and I haven't yet talked to Brian, but I just want to make sure they feel ready to give an answer. Since Patty wasn't here today, they weren't really ready to do that, but we will ask them at some point, as soon as they're ready, to tell us what they can about what they think the implications are from what they know.
So just so I understand this, we'll be working next time small groups. We'll be dealing with technologies, and the financials will not enter into
No,
that.
there will be
Yeah, there will
financials.
be. If you recall the diagram that we had up, we had the 2 bookends, and then we had technical studies, financial modeling, and the plan is to take the 2 bookends, which are both sort of the extremes, and put them together into a reasonable straw man starting point.
Okay.
We'll have a presentation next time. It's not just going to be, here it is. We'll have a presentation of the rationale, advantages, disadvantages, some of the alternatives that could be considered and that, are close in various sub-watersheds. But it will be a full, quote, hybrid plan. They'll break out into groups, and each group will come back with ways to make it better. Here's what we think, and it will have cost information. I have to
Range.
lean on
Ranges, yeah.
Stantec to commit to get the bookend cost. They're not going to be, design level cost estimates. They're going to be put into the framework of what they were at conceptual planning bookends. And then we'll have a basic cost for the hybrid with some trade-offs. We can do this, which is more expensive capital, less O&M, or this, which is more O&M, less capital, or we can do this, which is better, higher reliability, or we can do this. And tools for each group to make it better and come back and present your rationale for why this is a better case. And from that, what we're hoping to do is go away and understand better what you all agree on. I'm hoping that in the 3 plans that come back, there's something in all 3 of them that's the same.
we're gonna,
If not, we're in big trouble.
we're gonna at least understand the range of where we are.
But we'll take those agreements and put those together, and then we're probably gonna end up with somewhere between 6 and 12, 4 to 12 major or significant issues that we need to really focus on, to say this will work and that won't work. And that'll be the focus of the financial planning and optimization that goes through January and February.
Okay, if there isn't anything else, Sid?
It sounds to me like there'd be a lot of thinking going on next meeting, so it would be helpful if materials can be put onto the town website at least several days before, so we have a chance to review them.
Do our best.
Done. I have a motion to adjourn, Mr.
So
McGrath.
moved.
Second?
Second.
We stand adjourned. Thank you.